I think we can start the class, right? We have around 15 participants and more will be joining. Okay.
Yes.
Good evening, everyone. Today is the second session, live session of the module that is Researcher's Toolbox. Today we'll be learning about foundations of quantitative analysis, and the expert for today is Dr. Pankaj Chavan. Dr. Pankaj Chavan is an assistant professor at the Center for Education and Technology for Education, CET, IIT Jodhpur. He holds a PhD in educational technology from the Indian Institute of Technology, Bombay. His research sits at the intersection of education, technology, and design with a focus on learning analytics for teachers, technology enhanced learning, and design for teachers. His doctoral research, that is Teacherly, is a data-informed feedback system focused on designing student feedback system that captures students' real-time cognitive and affective states during lectures. And the system includes a teacher-facing dashboard that presents aggregate class feedback and enables educators to make informed instructional decisions such as revising materials, adapting pedagogy, etc. And he has also won the Best Thesis Award at IIT Bombay. And we are very happy to have Dr. Pankaj share with us his expertise today. So, very warm welcome to you, Pankaj, and over to you.
Thank you so much, Dr. Ramana, for the warm welcome. And I think there are almost 16 to 18 participants I can see, right? So, okay, so let's get started then. Okay, so the way we'll do it is there will be some kind of activities in between. So I hope that I'll be able to finish this session within 1.5 hours. Okay, I'll definitely try to do that. But if I overshoot by let's say 5-10 minutes, please bear with me. Okay, so let's get started then. So what we are going to do today? So today we'll try to address some key ideas that are associated with data analysis in quantitative research. So in the last session, I think you looked at qualitative analysis and what exactly different methods are and tools are. Right? So in this session, we'll try to understand and address like how exactly data preparation looks like, what exactly happens in descriptive statistics, what happens in inferential analysis. So this kind of things we'll try to do today. And these are the learning objectives that I thought I kind of try to address in today's session. So first thing is, at the end of the session, you should be able to critically examine characteristics or features of distribution of variables. So whatever variables are there in your research design. So you should be able to kind of understand and even kind of identify patterns to it, whatever data you are capturing. And then to support that, you should be able to utilize or use visual displays and numerical measures judiciously. So what do I mean by that? So basically the idea is we all of us know about pie charts, histograms, QQ plots, and maybe different other visualizations, right? So I'll try to kind of specifically highlight when to use which type of display. And with that, I hope that you'll be in a position to judiciously choose which type of visual display to go with when you have a particular type of data or a particular combination of data points that you have, right? And as we are talking about displays, so obviously it is important to apply good practices for clear and accurate data presentation. So that is what the next objective is. And towards the end, I'll also talk about use of inferential statistics. So specifically, I'll talk about t-test, but I'll just give a brief overview of which test, when to use, and all of that, right? So I'll try to do all of it in today's session. So I hope this seems interesting. So what are the learning goals? So one is objective, which I said, okay, this is what at the end of the session you'll be able to do. But then how are we going to do it? So to achieve that and to achieve the end goal. So basically the focus will be on understanding why to use a particular graphical representation or a statistical measure or a statistical test rather than the how of it. I mean, you can like open YouTube and if you just search movie SPSS programming, you'll get a lot many resources to go through how to conduct a particular test, t-test, ANOVA, one way, two way, multiple regression, ANCOVA, and all of that, right? So I'm not going to talk about the how part of it. I'm going to focus more on why to use a particular test, why to use a particular measure, statistical measure, and why to use a particular graphical representation. This is just one example that I'll start with, right? So, if I'm working in, let's say, an organization and I'm the CEO of the company, just assume that I'm the CEO of the company, okay, and I want to compare the salaries of employees across different departments in an organization, in my organization, or I can be a researcher who wants to kind of look at how salary distributions look like. So, which graphical representation, in your opinion, would be better for us? Anyone can just unmute and speak up. Any thoughts?
We are also monitoring the chat, so you can also use the chat feature to say either diagram 1 or 2 and along with the justification.
Okay, someone said blocks plot. I see Ujjwal saying box plot. I'll wait for maybe one or two more responses. So just to explain, this x-axis is salary in this histogram, y-axis is the frequency, like how many people are in this particular salary range. Here, x-axis is kind of departments and y-axis is the salary. And here, these legends basically are the different departments. I think Ujjwal saying box plot. Anyone who thinks histogram will be a better option? No one?
There is one response for histogram.
Histogram. So maybe just let Ujjwal and the other whoever has responded right now. Could you please tell me like why do you think a histogram would be a better option and not box plot and vice versa? Quickly.
Yeah, can I unmute and say it's easier than typing it out?
Sure.
Yeah, so at least for the histogram, I'm able to see like the frequency in numbers and like the department type. So I get the salary range information. I can figure out, okay, X number of people in, let's say, sales are in that, how many zeros, 40,000 bracket, and then further like going down with like the marketing side, there's that 70,000 one.
Okay.
So that's what I'm basing it on. I'm getting like frequency information as well, which is missing
Makes
in the
sense.
box plot, which is just department versus salary.
Okay. Okay.
So it's just like an added. Also, I think the histogram one looks prettier, which is how I base most of my data assessments too.
Okay. Okay. Yeah, I think. Yeah, that makes sense. Okay. I think Ujjwal or someone else also just now said histogram. If you could briefly say why.
Yeah, so I'd probably assume histograms box plot, primarily because if I want to get an answer about the segmentation across different departments of the salaries, it's a lot easier. Like it's very difficult for me to, for example, if I want to answer at what for sales, what's the average salary higher in what department? That's something I can't really answer through the histogram. Especially with outliers, etc., and ranges, etc., it's a lot clearer through the box plot.
Okay, makes sense. I think so. What we'll try to do is, I think I'll stop here for this activity, and at the end of the session, I hope that all of us have some answer related to this. Okay, not this, some other context. Then another learning goal is understanding why to use a particular statistical measure or test, like mean, median, mode. All of us know, but then when to use which, that we'll try to kind of drive that as well. And the last one is understand and apply good practices for clear and accurate data representation, right? So it's very important that we use accurate data presentations as well as everything is in place in terms of right from access labels to legends to what kind of visualization you are using. If you are using a type of visualization, what all kind of things that you can do with that type of visualization. So we'll also try to understand some good practices and how we can clearly, accurately present data. Right? So I hope that whatever this comic strip here, we don't get caught up in such kind of situation when we write our research paper. Okay. Right. So let's get started then. So I'll start with the big picture first. So in the last session, I think Dr. Navneet discussed about qualitative research and a discussion on quantitative and qualitative also happened, right? So let's try to kind of revisit that quickly and also try to understand if we are doing a quantitative research, then how does it look like? So here I have a research question. The research question is simple. How effective is an augmented reality app in teaching representational skills in chemistry? That is what my RQ is. So I want to incorporate augmented reality as a technology into the teaching learning process, and I want to ensure that the students' representational skills are better. And that's what my idea is. And that's why I think AR might help there, right? Because it's visualizations, 3D, 2D, and all those translations and everything is possible, right? So if I'm doing, let's say, qualitative research, how I would look at it. So I might conduct some semi-structured interviews and artifact analysis with, let's say, 20, 30 participants or even maximum 40 participants to explore their representational thinking. So let's say I'll give them AR app, they'll use it, and then I'll conduct interviews. I'll also go through their writings, whatever explanations they have by working on the activity sheet. I'll collect all of that, and then I'll try to make sense of it. So how would I make sense of it? I'll analyze the data. So what is the meaning of analyzing the data? So I try to connect it with the previous session where it was about performing thematic analysis to identify certain patterns. So here in this case, we'll look at certain explanations that students have, the conceptual shifts that has happened. So through interview, can we identify this kind of instances? That is what your analysis might look like. So once you have this kind of analysis, codes, themes, everything in place, we'll try to kind of triangulate, combine everything together, and also try to validate the interpretations with, let's say, some other researcher and all of that. And then based on that, you'll say, this is what we have understood from this. And based on that, something can be done in a particular fashion, right? So that is how inferencing kind of looks like in a qualitative research. Let's say if I'm doing a quantitative research to answer the same question. So what I might do is I might design a 2-group pre-post research study, let's say with 40 participants in each group. So I have almost like 80 participants in total. One group control, another group treatment. So treatment group gets AR, control group gets, let's say, a regular lecture and all, right? So that is how I'll design the research, and from there I'll collect the data. So data collection is what? I'm collecting pre-post data points from this particular setting. So how would I analyze the data? So simply what comes to our mind is, let's calculate the mean of the learning gain scores. So let's say pre-post data we have for both the groups. Absolute learning gain is basically post-test score minus pre-test score. And once we have these scores in place, we'll calculate the means. And then we'll try to kind of understand whether there is a difference between two groups or not, right? So that is at one level of analysis. If I want to inference something out of it, and then I want to say, like, this is how AR helps, or AR helps in improving representational skills. If I have to make that statement, some inferencing is needed. So how do we do that? So at the start, when we design this study, we write RQ like this, and then we say, my hypothesis is that with the use of AR app, the improvement in representational skills will happen in the context of chemistry if I use it, right? So inferencing usually happens like when you do hypothesis testing, and you have something called as null hypothesis, alternate hypothesis, and you say null hypothesis, basically there will be no improvement. If you are hypothesizing that, there will be. Alternate hypothesis is there will be improvement in representational skills with the use of augmented reality app. So your inference will be just to kind of focus on that we reject the null hypothesis that the AR app does not improve students' representational skills scores with the help of t-test. So we'll conduct this test and we'll say null hypothesis is rejected, meaning AR app has actually improved students' scores in representational skills. That is what we are trying to do. So that is how the qualitative part of it and the quantitative part of it looks like. If you are doing qualitative research, you might do it in the first way. If you are doing quantitative, you might do it in the second way, right? So this is what we have. The left one is qualitative, the right one is quantitative. So now let's focus on the quantitative part of it. So there has some change which has happened in this column, right? So what exactly we are doing here is, so the step one is we are producing data. From where we are producing data? So we are taking some sample from population. That's how we produce data, right? Once we have some data, we would try to understand the data. We'll try to analyze it, summarize it, make sense of it, try to identify some patterns. Can we identify something that is happening in a particular fashion? That is what exploratory data analysis or descriptive statistics look like. Then the next phase, once you do all of that, then you calculate mean scores or whatever other statistical measures you have. And using that, you basically try to identify like what is the probability that this, whatever you have been doing here, it's applicable for population as well. That's when the probability through t-test and whatever other inferential statistics that you conduct comes into the picture. And through that, you basically say, this is what the result is, and this is how the finding is, and that's how it can be generalized to a larger population from where the sample has been drawn, right? So that is how quantitative research looks. This is just another representation of that. So I just kind of thought like I'll do sequence wise, like how exactly it looks like. So the first step is you sample the population to produce data with which to study the population. So this is what the population is. Then you sample some data out of it. So that is what the producing data step is. Next step is you analyze or summarize the sample data or reduce the data. I'll talk about what exactly this means, but this is what descriptive statistics or exploratory data analysis is. Then the next step would be how we connect the sample statistics to population parameters. That's what I was talking about, probability. So here I'll not spend much time on this because I mean, even if you don't go into the details of this, it's fine. Even if you just understand probability is kind of playing the role here to draw inference from sample to population, that is enough at this point in time. And then you have some statistical test based on which you kind of say that this is what the finding is. There is a difference in two groups. AR has performed well, and all those kind of inferences you can draw by using some tests like t-test, regression, ANOVA, and all. Right? So that is what inferential statistics is all about. So this is the big picture in quantitative research that we have. Now let's come to the core of it. I mean the business of it. So let's say if I'm conducting this research, this is the RQ I have. How effective is an augmented reality app in teaching representational skills in chemistry? So that is what I want to investigate. So I'm using a two-group design, which is like pre-post design as well. So two-group pre-post design is something I'm using. I have one control group, one experimental group, and the hypothesis that I have is students who learn via AR app score higher on the test than those who learn via lecture. So that is what my hypothesis is, because that is what I want to investigate, right? So what I need to do basically, so here I need to basically make comparison of performance between two groups. One is control group, another one is experimental, right? So how can I make this comparison? So I know that at this point in time, like before I implemented the intervention, I conducted a pre-test, then I conducted a post-test. Difference between the two, if I take, I will be able to know learning again, right? Same for this group. And then I want to understand, is the performance of two groups different? That is the first thing. And then I also want to understand if the performance of AR group is higher as compared to the lecture group. That is what I want to do. So that is what the first part, right? So what exactly needs to be done here when we say that we are comparing groups? Because when we sample data from a population, we are having individual participants. We conduct pre-test, post-test of individual participants. Now here, the focus is shifting from individual to group. Now we are no more talking about individuals. We are going to talk about how group behavior or how group score kind of looks like. So how to do that? So we have, let's say, all pre-test, post-test scores and everything in place. So what we need to do is we need to compile and organize the data. So how do we do it? So that is what we are now going to look at. So once you produce the data, so you sample some kind of participants from a larger population. You collect the data, pre, post, and everything is collected. If there are artifacts, if you want to collect that in a mixed study, that is also fine. You collect all that data, and then you need to prepare the data. What does prepare means? So basically, here is one scenario, the same research study. So the research team collected pre-post data of both groups, control and the experimental, right? And the maximum score on the test is 100. So if someone can score anything, so maximum number is 100 for that score. Pre-test, post-test, I do. Now here is a sample data I have. Okay. So carefully look at the sample data, which is here on the right side. So this is student ID. This is the group from where they belong, and this is like pre-test, post-test scores and all of that. So try to identify what all issues are there in this data set. Can you identify any issues? As and when you identify, and you can speak. If you want to kind of just post it in chat, that's etc. (110) data error. Okay, yes, that's correct.
Sir, in the experiment, in the student ID 4, the post-test score is
missing. Perfect. So row 4, student ID 4, post-test score is missing. Student ID 2, the score is more than 100. That is 1. What else? Look at it carefully again. So two points, two kind of problems we have identified so far. One is missing data point. Another one is
Student 8 also pre-test is missing.
Student 8 pre-test is missing. Perfect. What else?
And student 13 is again 110.
Is again 110. Very good. What else?
Subramanya is writing 13. Can you unmute and like tell us more? What about 13?
So 13 actually the post-test score is 110, sir.
Okay.
So there you find the data right.
Okay. Okay. I think good observation so far. There is one more thing that we are missing out. Look at it again carefully.
40 participants it says, and data is only for 60.
This is sample. I've just taken like 16 participants. Yeah. Anything else which is problematic according to you? Could be problematic, even if it is not, but let's say could be problematic.
In some instances, the scores have increased very profoundly.
Yes, like
from 33 to 90. From
very good, absolutely. Yeah, I think good observation. Very nice. Okay, so for student ID 16, the score has improved from 33 to 90. That's a significant jump. Okay, so that could be problematic. I'm not saying that is problematic. That could be a reality that the student has really learned those skills well, that the score has improved significantly. Right? That's a possibility. But we also need to kind of like very careful about what exactly that data point looks like. I think you guys have identified most of the problems. I would say all of the problems that are there in the data set, right? So what we do first when we prepare the data, first thing is we do the validation. We check for accuracy. We check for completeness, meaning are there any missing values? Are there any errors in the data? Is there consistency in the data? And if we identify any of those problems, so when I say consistency, it could be, let's say, the jump from 33 to 90 is huge, right? So that is what consistency from that point of view, I guess. So once we identify those, we then correct the errors. If there are some outliers like 33 to 90, we might remove it. And we resolve inconsistencies in the data and we make the data foolproof. Right? That is what we do. So one example is, let's say there are errors like students 2 and 3 having pre-test, post-test scores above 100, which is outside the valid range of 0 to 100. So this need to be corrected to prevent skewed results, because this could be an erroneous value. It might lead to scores getting shifted to on a higher side. So if it could either of like experimental group, control group, doesn't matter, but in either of the group, it might skew the data points, right? So it will move the kind of average more towards the higher side. So that is a problem. So correct them by checking raw data sources. Was it a data error? So obviously it is more than 100, so flag for removal. That is one thing that we get. Second is the student 10, which one of you rightly identified, has improved from 33 to 90, which is an unusually high gain, right? And which may be an outlier. So we have to carefully look for the outliers and evaluate to see like if they represent true observations or if there are kind of errors in the measurement itself, in the logging, data logging, or whatever that possibility is, right? And we'll see about more about this later in the session. But that outlier should need to be taken care of. Next thing is consistency. So like missing values are there. Right? So for student 8, pre-test score is missing, student 4, post-test score is missing. And then how to deal with this? So one simple way is you just delete that entry and don't consider that student data point in the analysis anymore. That is one possibility. If there are few cases, right? In that case, what you do is you impute the data, right? And you impute like means what? You calculate the average and then put that average value for that student. Correct? That is one possibility that you have. So that is how you can impute a value based on average pre-test data if there are few cases, right? And then if you're looking for post-test, because post-test is like after intervention something has changed, right? Whereas pre-test is kind of at the start. So using some average value there might be okay. Even not great, but it can be considered okay. But let's say when you have like post-test, the better option is to exclude it completely. If you don't want to exclude and if you want to kind of consider the data, you can impute based on similar students. Right? So pre-test score similar and even other parameters if you have kind of identified, let's say their previous scores, prior knowledge and all other kind of things. And in that case, you can compare and accordingly impute the data based on the similar students, right? So impute is basically calculate the average and use that value in the for that particular pretest or post-test. Then there is another problem of duplicates. So basically, you need to eliminate the duplicates. So student 16 appear to be duplicate of student 10. So remove duplicate entries and keep only one entry so as to avoid the biased results, as they may give some students data more weight than others. Say we have duplicates where students have scored very high in AR group. Then obviously what is happening is more weight is given on those kind of students' data points, which are actually problematic, right? And it's in duplication, it will kind of influence your data points and hence your analysis and the findings that you come. So that is what compiling and organizing data is all about, right? So that is what we have been looking at. So now what is the next thing? So I went through some of your, I think, responses to a discussion forum activity where we were asked to kind of design RQ, identify research design, and what kind of data you will collect, what you will do with that, what kind of analysis, finding, and everything, right? So I mean, I liked it, and most of you have like a very comprehensive plan, so that's a good thing to kind of know, right? But then I've seen like some cases where it's like calculating the pre-test, post-test was also kind of part of it, right? So one obvious step and the larger step is we calculate the mean of learning gain scores. So we first calculate the learning gain post minus pre for both the groups, and then we calculate the means. But the question is, like, only mean scores, is it the only descriptive statistics that we have? Is there anything more than that we should look at as a quantitative researcher? So that is what I think someone has posted standard deviation. Very good. So the standard deviation is one of the important factors that we should be considering. So what we'll try to do now in this part is we'll try to see what happens in descriptive statistics and descriptive analysis part. And we'll try to see how analysis, summarization, reduction of sample data happens and what other different things are there in the descriptive stats part. So we are going to talk about three things. So one is distribution of scores, because we are talking about pre-post, so I am contextualizing it that way. We are also going to talk about mean or other measure of the center. We know mean, median, mode are three different measures of central tendency. And we'll also talk about standard deviation or other measures of spread like range and even IQR, interquartile range. And these two, three things we are going to discuss in this part. Okay, so let's start with the first one. Now, what you've done is you conducted the study, pre-post data is captured. Now you have you organize the data, compile data, remove missing values, addressed all the errors, and all of that is taken care of, right? Now you calculate the learning gain. So there are different ways of calculating learning gain. The most simplest is you take absolute difference. I mean, you take absolute learning gain like post minus pre. That's how you get the score, like how much improvement in score has happened, right? So if you are sure that the pre-test and the baseline of both the groups are kind of similar or they are equivalent enough, then using this kind of learning gain metric should be a problem, right? So let's assume that we do this. Okay. Now here are like I'm going to show you two scenarios. Okay, so here is scenario one. Right. So this group one here, and there is group two here. So let's assume this is control group and this is experimental group. What are your observations? Anything, I mean, whatever you can observe from this. What are the first impressions that you have when you look at this data points? So x-axis is scores, y-axis is basically the number of like frequency. How many students got a score in that particular range? So let's say 8 to 9, this many kids, and 9 to 10, this many kids. Like this. Any observations?
One thing is that scores have increased in the experimental group. The number of students, as in light of how much they have scored, that frequency has increased.
Okay. So that's a good start. Like you are trying to now make sense of the data. That in control group, if you look at the distribution, the more data points are there on this side, right? So we're 10 to 16. So maybe improvement is more. If someone says Q is changed, what does that mean, Kaushik? And mean is 9 and mean is 11 for control. Very good. Perfect. So what is the meaning of skew is changed?
The points which are many people have scored in the experimental group towards higher grades.
Okay, so the improvement is more, is what you are trying to say, right? Okay. But then if you have to talk about the shape of it, right? All of us know bell curve, right? All of us know normal distribution. What do you think? After looking at it, is it like skewed, normal? What is it? Someone said, yeah, Gaussian, normally distributed. Yeah, very good. Okay. So both groups can be considered as normally distributed here. Okay, at least visually we can say that, because let's say this curve that you see here, this probability distribution function. So here we can, based on that, we can identify that this seems like normally distributed data points in both the cases, right? The distribution is normal. Now I'm showing you the second, another scenario. What is happening? It's completely, I mean, a similar context, but different data points. Makes sense. Any thoughts in terms of normal distribution, scores? Experimental group is bimodal. Very good. Very good. What does that mean?
There are two separate.
There are 2 peaks.
Okay, there are 2 peaks, so there could be 2 different groups, maybe. We don't know. And these 2 different groups might have been behaving in a certain fashion, right? So that is a possibility. So bimodal, that's a correct answer. It's like basically you have like 2 different groups that you can identify clearly from it. So that is one part that we have, right? But in terms of normality, what do you see? Are both of them normal or normally distributed?
No, the first one is normally distributed, but the second one is not.
Yes, perfect. So one group is normally distributed and other is non-normal, right? So the distribution here we see is, in the first scenario, both groups are normally distributed. In the second scenario, first group is normally distributed, second one is non-normal, right? So usually what we hear is this, like scenario 1, where both the groups are not, I mean, whatever data points you have, distribution you have, if it is normal distribution, then you do parametric test. In our case, we will do t-test. If the distributions are non-normal, then we might go for non-parametric test. One example for like parallel for t-test is man-Whitney test. Okay, that is what we will do, right? Okay, so what it tells us? It tells us 2 things. One is histograms is one of the visual methods to test normality. So at least you can make sense of the data. It's important that you go through the data, you identify how exactly it looks like, and what exactly the data points are, how are they distributed and all of that, right? So one is you can test and at least assume something related to normality by just looking at the histogram. That is one. Another point is you can also identify some potential outliers. So let's say, for example, instead of this histogram, if you don't have these 3 bars present here, okay, let's assume that these 3 bars are not here, only this bar is present. So that can be identified as a potential outlier, but it need not be. But you can definitely identify just by looking at the visuals that, yeah, maybe there is some outlier which is present here, right? That is one part. Then you can also use some statistical measures. So one is visual part of it. Second one is you actually use some statistical measures like a Shapiro-Wilk test and all of that. And there are multiple such tests that you can identify. You just put the data set and it tells you whether the data is normally distributed or no. So one is visual aspect of it. Another is kind of statistical aspect of it. That's how you can test for the normality, right? But now the question is it the only solution? Shall we just say, okay, it's normal distribution, do parametric test, t-test. If it is not normal, then do manual test. What do you guys think? Is it the only solution? Yes, no? Remove outliers, yes, okay, that could be a possibility. You remove the outliers so that your data becomes kind of close to normal distribution, if not normal distribution. Yes, what could be next? Collect more samples, very good. Yes, that is another thing that you should do. Or you can do. I'm not saying necessarily that has to be done. If your experiment is like very costly, let's say, effort and cost is on the higher side, maybe that is something that you may not do. Right? What else?
It makes sense of the data why it is skewed, because if I'm seeing that, that's a typical pattern I would see in the math assessment paper, wherein the first few graphs would be for abstract questions and the last one would be for a word problem solution.
Okay, okay, very good, very good. So I think that's how you're connecting it to the context and how exactly it might look like. Very good. Okay, but then shall we just go ahead and say not normal parametric, not normal non-parametric? Is it the only solution? Let's see. Okay, so why do all of us love or like normal distribution? Mostly because all the parametric statistical tests that we know of, such as correlation, let's say Pearson's product numerical correlation, or student's t-test, ANOVA, multiple regression, and whatever other tests that we can think of, right? So all these tests work really well for the normal distributed data, right? So someone said log transform or use CLT. Very good. What is CLT? Usually?
CLT would just be the central limit theorems. If I have a big enough sample space, usually we assume it to be greater than 30. I'm assuming almost everything would behave as normal distribution.
Perfect. So the point is, I think, which Felix mentioned, that collect more samples. That's what essentially it is. Increase your sample size so that even if the data is little skewed, it shouldn't be a problem. Even if it is not normal, you can definitely run the test, because the means of the samples and all of that, if you plot, it will be a normal distribution. But let's not go there, right? That is one possibility, that you use CLT, collect more data, and use all these tests there, right? So reason one, why your data is not normal. So either your n is very small, so left side is basically small sample size, right one is larger sample size. So that is one major reason. Another could be like there could be some missing data, some measurement error, some data corruption, some outliers present, because of which the data is getting skewed, right? So that is one possibility. So you remove outliers, remove those missing data points, or impute those, and kind of remove the rare events from the data point, but logically, not like just you remove it. Right? The third thing is there is a long tail, meaning the data is really skewed, right? And it's completely skewed, and you can't do anything related to that, right? So that is what the challenge is. Okay, then what to do? So these are different possibilities that you have. So either you increase the sample size, find and reject the outliers, use some non-parametric test like we just talked about, or you can sometimes use a transform to make your data set normal. I think Ujjwal mentioned log transform or using CLT. So log transform is one of the transformations you can use, but there are others as well. So what is basically data transformation? So it's a statistical method for converting raw scores into another type of scores. So it's no more a score out of 100. Okay, it's something else. Without affecting the original interpretation of the data. Interpretation will remain same, but the scores will get transformed into another type. So then it can be used to improve the shape of the original distribution by reducing its skewness, and hence you achieve the normality and run all the parametric tests that we have. Okay, this is the theory part. How does it look like? Here is one example of transform, right? So log transform is one. I'm not doing that, but here it is something called as square root transform, right? So what is happening here? So this is on the left side is your original data set. Okay. Then what you do is you reverse the data set, meaning you identify the maximum value, and each value from that maximum value you subtract each value that is there in this data set. Okay. So once you do that, what will happen is, so let's say here the maximum value is 80. If you subtract 80 from 80, it will become 0, right? So obviously your data will kind of get shifted towards the left side. So what you are doing is you are basically subtracting all the values from the maximum value in the data set, and then you are taking a square root of it. So if you take the square root of all this reverse data points, what you will get is normally distributed data. So once you get this kind of thing, then you run the parametric test. Now you might question, okay, but now it is like maximum score, the student who scored less now are getting more scores if we reverse it. Never mind, because at the end of the day, what we are looking at is the group. We are not looking at individual students. That's what I said at the start. We are shifting the focus from individual to the group. That is what essentially we are trying to do here. So that is one form of transformation. Let's say square root transformation, from where you can transform skewed data into a normal data set. Okay, so that is how it looks like. So what are the takeaways related to the first thing, which is the shape of the distribution? So one thing is use visual methods, either histograms or there are QQ plots as well, or use statistical measures to check for normality of the data. So Shapiro is one, column is another. Right? If data is normally distributed, then use parametric test. That is what, which is like everyone knows this, right? But if data is not normally distributed, consider alternatives. You can directly go with non-parametric test. That is the first solution that comes to mind. But then you can also think about increasing sample size. If it is not possible, then you try to see whether there are any outliers. Can you identify and remove those outliers so that measurement errors are reduced and hence the data becomes normal? Or try to apply some transformations like log, square root, box, and all of that to normalize the data. Now, if let's say your transformation works, then you can go ahead with parametric test any that is suitable for your research. If not, then you have to go to non-parametric. There is no option that is now remaining, right? But this is what we should be kind of trying to do as much as possible, is what this kind of takeaway from the shape of the distribution kind of is, right? Now try to look at the another part of it, which is mean, right? Which is the average or central tendency, measure of central tendency and all of that. So in our context, we are talking about learning gain scores. Learning gain scores of the group using AR, learning gain scores of the group who is not using AR. Let's take a look at the data that we have. Before that, all of us know this, right? So mean is what? You just simply add all the values, divide by the number of values. Then you take median is the middle value, mode is the most recurring value and all of that, right? So all of us know this very well. All of us know mean, median, mode. All of us studied in all of this in school, right? So all of us know mean, median, mode. Quickly do this. So calculate the mean, median and mode of the following learning gain scores. I'll not ask you to calculate, I'll calculate for you. So these are the mean, median, mode values for this data set. So let's assume that this is data set of one group, either control or experimental one. So if I have these values, and if I ask you that you have to pick one number to communicate the center of the distribution, which one would it be? And why? Is the question clear? Okay, mean, Mercy is saying mean. Median, Ujjwal is saying median. Perfect.
Medians.
Okay. What about others? Which one would you go for? Quickly in chat. Marina is saying median. I need few more responses, at least 2-3 more. Mean. One more. Median. Perfect. Okay. So now we have like almost 50-50. Okay. Half of you are saying median, half of you are saying mean. So whoever has said mean has to kind of convince the group who has said median, and the group who has said median has to convince the other group. Anyone can start. Who wants to go ahead from, let's say, median group?
I would say median. Why? Because see, if there is some outlier, so the mean will get changed, obviously. So hence, I feel like median should be the right one.
Sorry, go ahead. Say it again.
If there are some outliers coming into picture in the data,
and which are those outliers?
In this case, 70 would be the 70 would be.
Okay. Yeah. Someone from mean group who is saying that mean is a better option. Go on. Whatever, there is no correct, wrong. We are not trying to look at that. I'm just trying to understand the reasoning behind it. Why do you think mean is a better option? No one?
So I feel mean should be the option because actually the data which we have got, it actually represents the middle value because median is, but it can have shifts. अगर frequency ज़्यादा हुई किसी number की, तो median can shift.
No, but frequency is more. Median is the central value. the center point of the data set. So let's say we have 20 points, so center of that, whatever that value is median. Okay. So I think one of you rightly identified that median should be used because there are some outliers here. So 53 and 70 can be considered as outlier. Would you still prefer median as the true representative of the center? If I remove these data points, so I identified that these are the outliers, and I remove these data points. In that case, which one would you use?
What will be the mean median mode, sir, now in this series?
Kind of like closer in that sense. Okay, that is one way to look at it. Another way is just look at the data points. And this, the data points which are like very far from other data points have been already removed, right? Then what would you do? So isn't 3 or 4 also outlier? Yes, very good. So that could be outliers. Yes, so we have to look at. So that's essentially the point. So here 53, 70, maybe you are able to identify. Those could be outliers, but these are all potential outliers at this point. What if I do this? Here we have only this value, so you can see like 3, 4, and 53, 70. What if I do this? What if I multiply this by hundreds and tens and all of that? If you have a very large sample size, how can you identify such values which are called as outliers when the data points are significantly large? Any idea? Quickly, if not, then I'll move forward.
Can standard
sorry, yes.
Kind of standard deviation, does it help? Like
standard deviation, okay. Someone said box plots as well to identify outliers. Standard deviation could be because you can see, but standard deviation is more of like how the spread is. Right? So that's how you can say like it is very spreaded and all of that. You might not be able to pinpoint that this could be an outlier. Right? So that is what essentially box plot does. Right? So box plot is you order the data and then you plot it and you then say like 25. This part is basically the first part is 25% of the data. The last part is 25%. The middle one is 50% of the data. So then using box plots, you can identify where the outliers are. So like some of you said, just 3 and 4 could also be outliers, and 53, 70 could be an outlier. So this data or this type of data when presented using box plots, you can clearly identify where there are outliers in your data set or not. Then you take a call whether you want to remove it and how you want to kind of adjust further, right? So remember at the start I said like we'll come back to this part. So that is what I meant. So you can't just looking at the data points identify what is outlier, what is not. You need some method, some tool, some technique. So box plot is one of the techniques using which you can definitely identify outliers. So there is some logic behind what can be called as an outlier, which is written here at the bottom, like on both sides. But I'm not going to do the details of that. The point is box plots will definitely tell you whether there are outliers in your data set or not. Potential outliers. Then there is something called as extreme outliers. So extreme outliers we should definitely get rid of, but potential maybe we can take a call based on the entire data set. Right. So takeaway is this for the center or central tendency measure, that use mean and standard deviation if data is normally distributed. Use median and interquartile range if data is skewed, and check histograms first before deciding. Right? So that is what you have to kind of always look at when you are analyzing the data, summarizing it, and describing it. Right? Now let's look at the standard deviation part of it, which some of you already talked about. So again, coming back to our AR and lecture design, here we have like two distributions. The green one is control group, the blue one is treatment. What does it tell you? And this is related to standard deviation. So I'm explicitly saying that out. Any thoughts? These three are like three different possibilities. So let's say this is experiment 1, experiment 2, experiment 3. All the three experiments had AR and no AR. What can you comment when you look at these three different graphs or distributions, not graphs? Okay, let me help you. Any observations related to mean? Okay, let's first do this. Is it normal, non-normal? Normally distributed, perfect. What about mean? Are the mean values same, different across three cases? Are they same or very different? Same mean? Someone is saying different. Okay, okay, same. Okay, if the means are same, then what is different? Look at the shape of the distributions. Where you can confidently say that AR is improving the representational skills of the students. Case 1, 2, 3. In which case you can confidently say that yes, it is improving. Case 3 is confident. Why? Felix, could you please kind of elaborate briefly?
The overlapping is very less in case 3. Sir.
Okay, so overlapping is very less in case 3, whereas it is highest in
case 2.
Middle one, right? And kind of less in the first one, right? So this overlap is higher because of what? Because of
maybe error.
Yeah.
Any error?
Because of error, not really. Could be, but not really error. It says that the data points are very spreaded away, right? That like the spread is very high. In the last case, in the third case, they are kind of tightly bound around mean, right? So all the data points are very close to mean. Here they are somewhat spreaded. Here the spread is very large, right? So that is what essentially standard deviation is, right? So when you see in a research paper, you see like experimental group students mean score was, let's say, learning gain was 15, and then in the bracket it's written standard deviation was this, right? Then control group this, and again standard deviation is kind of why? Because it tells you that okay, the mean score could be, let's say, 15 and 13, but between 15 and 13 of experimental and control group, standard deviation is how much. So that is what essentially is important. So in the paper, when you write standard deviation, it means that your standard deviation is either very small or it's very large, which tells how significant that difference is. So here the significance will be there. Here also there will be different statistically significant difference. Here could be here less chances of getting that, but here you will definitely say that, right? But there is one more thing, that how different these two are, right? So here if you see the overlap is increasing and here it's a like very high overlap. So now here you can say that they are no more different, but here you can definitely say they are very different from each other. So the gap between the two values and how the overlap kind of looks like, how many students from one group have similar values as compared to other groups. That is what essentially the standard deviation kind of tells you. If it is very small and the kind of mean values are far apart from each other, we can say that the difference is very strong. That is what essentially effect size is all about. So I'm not going to talk about effect size, but at least keep that in mind whenever you kind of write your papers, read about effect size, what exactly it is and how you can kind of work on that. Yes, you raised a hand.
Yes. So just a question here. So for case 3 specifically, this sort of conveys that when my scores are closer to the mean, my technology that I implemented works. So is that a good inference for me to state? Because it sort of also clarifies that only when scores are near the mean that technology works, because I can't really talk about scores are less.
Okay, not really, because let's say, for example, here you are saying that because you see that the values are tightly bound around me. Okay, let's assume that this is the case. Okay, they are not tightly bound around me, but this blue curve, you shift it little towards the right side. Okay, so in that case, even if the values are spreaded, not necessarily means that technology is kind of helping very much, and because of that the values are like very close to each other. The point is, when you use technology, between two groups what is happening, right? So if you kind of shift it little towards the right side, and if you keep shifting it towards the right side, you can say that technology is working and it is effective in its own sense, right? And when this gap between the two increases with less and less overlap, your effect size is higher. I mean, the strength of whatever the intervention is, to what extent it works. So the strength of or the degree of working of that intervention, you can say, is high. So that is what essentially this effect size kind of tells. But not necessarily that if the values are very close towards the mean, it means that the intervention is working well. It is just that all the students are kind of having a similar score which are around mean. So I think that is what I can, at least that's what I think. Maybe I'll think about it more. What you are saying could be like that, but that's what my opinion is. It couldn't be like that. Does that answer the question?
Yeah.
Okay. So what exactly this is? So this is nothing but spread, which is standard deviation of, right? So a measure of center gives us an idea of single value. It tells you that you can use that value to talk about your data. You can say the average of control group was 12, average of AR group was 15. So with single value, you are able to talk about the entire distribution. That is what central tendency measures does for you, right? Whereas spread tells you how the rest of the values are arranged around them, right? So in other words, how the variability kind of looks like. So we looked at like here there is low variability, here medium, here very high variability, right? So these three questions kind of this answers. Like how different are the values in the distribution compared to mean, right? So if we just look at here, all the values in the distribution are not very different from the mean. Whereas here, the mean is here, but rest of the values are like far spreaded, which means that the values are very different as compared to mean. That is one answer that you can get. Second is how well the mean value represents the distribution. So here, the mean value is quite very well representing the distribution, whereas here it is questionable. It is kind of okay, right? Because all the values are kind of near to the mean. So that's how you can say that the mean value here is kind of representing the distribution very well, right? And then based on this, you can identify at least visually how two distributions are. And through the values of standard deviation, from there also you can infer. That is a little abstract. But when you do it visually, you can definitely identify how the spread kind of looks like, right? So what is the takeaway? So takeaway is you can either look at the max mean to identify the range, that is one. Interquartile range or IQR goes with median, right? And it is the difference between Q3 and Q1, the center part that we looked at. And last but definitely not the least, we have standard deviation which goes with the mean. So whenever you are like, let's say having normal distribution, you use mean along with that standard deviation goes. If you have non-normal distribution, you obviously will use median because it's a skewed data set. And with median, mostly IQR kind of goes to understand about how the data is spread. Right? So that is how we can think about distributions and descriptive statistics in its own sense. Right? Okay, so let's come back to the scenario that we have looked at. And two groups we have. One is control, one other one is experimental group. The data is normally distributed. And then we want to conduct a parametric test on this. Right? So what I have here is, now we are moving towards the inferential statistics part of it. So on the left side, I have the data set. So the data set is arranged like the first column is participant ID. The second column is treatment group learning gain scores. Third column is control group learning gain scores. Right? Then I have put all of this into a software called Jamovi. Right? So Jamovi is an open source software using which you can do different kind of statistical analysis and all. Right? So you see here the way I have done it. So first thing is the treatment groups values are pasted here, and below this, which is not visible, is basically all the control group values that we have, right? So once you upload all the values here, update here, and then you go to t-test specifically here, for example, you will see some options here. So there are three options. One is independent samples t-test, second one is pair, and third one is one sample test. So what exactly these are? So independent samples is what? So we have two groups which are independent of each other, experimental and control. That is what, and on which you want to conduct the t-test. So that is what independent samples t-test, using which you are comparing treatment and control learning gain in our scenario. What is paired sample t-test? Is basically if we are comparing pre-test and post-test within the same group. So let's say you don't have control group and all of that. You have a one group pre-test, post-test design, and you are just comparing how the improvement is from pre-test to post-test when the intervention is implemented. But you don't have another group to compare with, right? In that case, you will use paired sample retest. Why paired? Because it's the same sample, same kind of students. You are testing them before, you are testing them after. So you are basically whatever you are looking at is in the same pair of data. That's the reason you will do paired sample retest there. So that's how the comparison between pre-test and post-test of the same group happens. One sample retest is, so let's say you have one group only, and their learning gain scores you have, but there is some benchmark value. So there are some previous studies which have been conducted, and you compare that with that particular thing. So that is one sample retest. So some existing data set you have, you collect some data, you compare your data set with that data, and that is how the one sample retest kind of works. So the tool name is Jamovi, Jamovi. Okay, perfect. Right. So now what I was talking about is this. So how to do a t-test here? All this data is kind of uploaded here. First column is your group. Second column, learning gain scores. Treatment group, all the scores on the second column. And below this, we have control and all the scores for control. Right. Then using Jamovi, you can do all different kind of descriptive statistics here. I have shown here, right? So for example, you can do this descriptives where you can have like how many number of participants, are there any missing values, then what is the mean?
Yeah. So there is a query, like somebody is asking what is a gain score?
Okay. So learning gain score is basically, in our experiment, what we did is we have two groups, right? We have experimental group, we have control group, and we are saying AR will improve the representational skills of the students. So what we are doing is to identify whether that is really happening. So we are conducting pre and post tests. So what is a pre-test? So before implementing the intervention, we are conducting a test. So the same test is given to control group where lectures are happening and to the AR group where augmented reality app is implemented. But it is happening before you implement all of this. Okay. So before your research starts, you conduct a pre-test. Then you conduct your research, you implement AR, you implement lectures and everything. Then you again conduct a post-test, right? So this post-test is after the intervention is done. So you have now pre-test and post-test. So you have pre-test, post-test scores for control group as well as experimental group. Now what you will do is, you want to know whether students have improved or not. How can you identify? The simple thing is, you just subtract the post-test scores from pre-test scores. So post minus pre. Post-test score minus pre-test score for control group, post-test score minus pre-test score for experimental group. Once you take the difference, that is what exactly learning gain is all about. Right? So learning gain scores are, let's say, some student has scored 10 in pre-test and 15 in post-test. The learning gain is 5 for that student. You do the same thing for all the students across groups, and then you identify learning gain scores for that particular set of students, right? So here essentially student 2 has improved by 5.33, 3 has improved by this and all of that, right? That is simplest way of doing it, right? There are another ways like normalized learning gain. I'll not discuss about it, but I'll share some resources so that you understand what exactly normalized learning gain is, when to use what and all, right? But essentially the point is, it tells you how much improvement has happened before intervention, after intervention. Does it answer the question, Sayyid? Am I clear on that? Is there anyone who is not clear? Okay, perfect. Okay, so what I was saying was this, that you have this learning gain scores, then you do this descriptive statistics and you get like mean, median, standard deviation, everything here, right? And I also mentioned about Shapiro-Wilk and all of it, right? So you can also conduct normality tests here. So that is what this tool can do for you. I'll come to you, Felix, just a minute. So another thing is, you can also plot histograms and see how the distributions are they normal, not normal, are they very different from each other? So visually you can do that. Then you can also plot box plots where you can identify outliers, and then you can either reject, remove those outliers from your data set. That is another possibility that you have, right? So like I said, this box that you see here is basically 50% of the data points. This lower line is basically 25%. This is 25%. These are the data points. And this dot, the square dot here is basically the mean. So let's say here it also tells you that your mean and median is kind of very close to each other in both the cases, and that is also visible here. So it tells you the data is normally distributed. So you are kind of trying to triangulate everything. So you have visuals, you have this test and everything. You also identify outliers. You also see how the distribution looks like. Can you make sense out of it? Can you see what does this higher data points here, like higher learning gain scores might mean? What does this lower learning gain scores might mean in the control? So all of those kind of things can be made sense of. Yes, I think Felix, you raised your hand. Is there a question?
Sir, for participant ID, it represents one student. So
yes.
When one student is in a treatment group, will he be absent in control group? Because we see the participant ID, one participant, and we have their score in both treatment and.
Okay, perfect. So the point is here, the participant ID, I have written it like this, but this is only treatment group and then another student. So basically, this is like one student. So let's assume it like 1T and 1C. This is 1T, this is 1C. Okay. Does it answer? Sorry for the confusion, but the point is, this is student 1. This student is not same.
Yes, then it should be pre-value and post-value.
Kind of, yes. So, sorry for that. I think somewhere I missed it. But this shouldn't be there. So basically, this is student 1. This is another student. This is different student. Okay? These two are different students.
Thank you, sir.
Yeah. Okay. Now, what I'll try to do is I'll just show you this, and then I'll move to the tool, and I'll quickly demonstrate what it can do for you. Right? Okay. So here I showed you about descriptive statistics and all of that. Now, about inferential statistics, what it tells you is all of this, right? It gives you like group descriptives, like what is an N, mean, median, and all of that, standard deviation, everything. And then here is a sample t-test t-test result, right? So it gives you a lot of things here. So it tells you what is the mean difference. And here you can see there is a difference between the mean scores of treatment and control. And yes, I'll do that. I'll show it in the tool, and then I think that will be even better in that case. Okay. And it tells you a lot of things. So there is one more thing which I mentioned earlier, which is effect size, right? So 1.11 is the effect size. It means that the difference between the two groups is stronger. I mean, that is significantly different to t-test ne bol diya, but how strong that difference is, that is what effect size tells you. So how different the means are from each other. So that magnitude is told by the effect size. So that is what another statistical measure that you can include in your analysis. That is what something that you can do. Now what I'll do is I'll quickly shift to the tool now, and I'll quickly show you what it can do for you and how you can analyze data using the tool. Okay. Is my screen visible?
Yes, sir.
Okay, perfect. So this is what essentially I was talking about. So here, what you have is this first variable is group. Okay. So you have added all the data here. So you have defined this group as one variable, and then your learning gain scores is another variable here, right? So obviously, group is a categorical variable, which is also called nominal. Like it has two groups, treatment and control. So from drop down, I have selected this nominal. Then here you have this continuous variable, which are like values and all of that. That's the reason I selected continuous. And this is what two variables that you have in your data set, right? So you add this data, set the variables and all of that. Then what you do is you first want to, let's say, analyze the data, but you want to do descriptive analytics. So that is present here in the exploration stage, part of the tool. You just go here, click on descriptives, and you will see options here. So what are the variables? So the variables are basically learning gain scores, because that is what is changing, is taking up different values. Then group is what is you want to split by, because treatment and control are two different groups, right? And you want to compare the two groups. So you move this group variable into split by, and the learning gain scores into the variables part of it. Once you do it, then you can see here you have a lot of options. So let's say statistics. So you can choose like, let's say, mean, median, and all of those values can be selected. And once you select this, all of those will appear here in the table on the right side. And you can just copy this table directly. So you just right click on it, you can copy the table and paste it in the paper editor. Okay. Then you can also have like different measures like standard deviation and all of it. You can also test for normality. So let's say I'm clicking on the Shapiro-Wilk test. It will automatically come here and you'll see that the Shapiro-Wilk test is showing that p-value is 0.979. It means that it is normally distributed. If this value is less than 0.05, the distribution is not normal. But now this shows that the distribution is normal, right? So that is one part of it. Another is you want visual displays. So what do? You click on histograms. You will see histograms coming up here on the right side, and then you see you are getting comparison of it. And then if you just click on this density, you get this probability density function. So it basically gives you like a distribution, like we have normal distribution, all of that. So it tells you like how this kind of looks like. So that shape clarity is better in this case. Then you can also have bar plots. Box plot is also a possibility. So you just click on this, you'll get the box plot here on your screen. Right? So essentially these are the same things that I showed you on the slide. Okay. So once you do your descriptive analysis, then you move to t-tests. And like I said, we'll do independent because there are two different groups that are independent of each other. That's the reason I'll choose independent samples t-test. Then I will choose the variable. So what is my dependent variable? So learning gain scores is dependent because it is changing as I'm using either AR or lecture. So I'll move this to dependent variable. I'll move the group to grouping variable. Once I do that, I'll go here and I'll see what kind of test I want to do. So this is already a sample t-test that I have. My data is normal, so no need to change anything. Students t-test is already kind of clicked here. Then based on my hypothesis, I can choose what needs to be done. So here, what hypothesis is saying is group 1 is not equal to group 2. So my hypothesis is that there will be difference between the groups. When I'm saying group 1 is greater than group 2, I'm saying that my experimental group is going to get higher value as compared to the other group. And same is applicable for the third one. So it is one and the same in that sense, right? So you can choose it likewise. So what does this gives you? So this gives you the result where you can see the result that I showed you on the last slide, where you can get like learning gain scores, the p-value is less than 0.05, which is like for 95% confidence level, which means that 95 out of 100 times whatever the difference that you see in the scores is because of the intervention, not because of something else. Either it is lecture or whatever that AR thing that you are using, right? So this is what all of this interface can do for you. So I just wanted to give all of you a quick overview of how this geometry kind of looks like and what you can do with it. Now what I'll do is I'll go back to my slides, and before I move forward, I would like to ask, are there any questions related to Chavan? Any questions?
No, it's not related to Jamovi, but in general. Sir, while we are choosing a sampling size, how do we decide like whether the chosen sample size is appropriate or not? So because in my research, whatever I'm doing, I have collected number of participants details were like 25 around. But I was not sure whether that sample size is sufficient or not. How do I decide that?
Okay, so there is no single answer to it and there is no single correct answer to it. That's what I think. But usually something more than 30 or something more than 40 kind of is okay, because then using those data points somewhere, if let's say you get normal distribution good enough, but if you don't get, then you can go for non-parametric test. But I think 30 to 40 can be considered as a ballpark value where at least this many sample sizes are needed to conduct any statistical test. Because then the data points that you have, if those are below 30 and 20, then whatever this kind of analysis inferences that you are drawing, they are not strong enough, because the statistical power itself is now going down, right? You have very less observations and you are trying to kind of bring out something from those less number of observations, and you are talking about the population, right? So with sample size of 15, 20, it becomes not much sense to talk about t-test and all of those kind of things is what I think. But if you have like sample size above 30, 25, 30, I think that should be good enough. So even if you have 25, no problem. If your data is normally distributed, go ahead with parametric. If not, then I think you try out transformations. If that is not working, go ahead with manual. So yeah, that would be my answer. But there is no single correct answer that this has to be the sample size. If the distribution is there, yeah.
So when you say 30, it is including both control and experiment groups?
No, one group I'm saying. One group.
Okay, sir.
But that is just a ballpark value. I'm just saying that maybe 30 more than 30 is kind of okay. But as you collect more and more data, that's always better because you go more closer to the normal distribution. But something around 30, 35, 40 is kind of okay. Then you can use any statistical test in relatively. You can be confident about it.
Okay, sir. Thank you, sir.
Okay. Right. So now what I'll do is I showed you the interface, how Jamovi works, what these different kind of things are. Now I'll show you some examples from actual research studies that has been conducted. Right. So here is one study. So this study is also about augmented reality. So augmented reality to teach lines and angles is what this study was trying to look at. So what they did, they actually gave it to two groups, right? And those two groups were like, one group was called treatment 1, where students worked on ARR individually, right? And group 2 was called treatment 2, where they worked in groups, in a pair of 2, right? So here you clearly see that there are two groups. One is dyads, one is individuals. And you see how the data is plotted. So I wanted to show you one example of how you summarize your data and how to plot your data. So here you see this dark blue is basically pre-test, this one is post-test. And the data for dyads and individual groups is also kind of plotted next to each other, right? And there is one more thing, which is this error bars, which is basically about talking about how the spreaded values are and all of that, right? And then you see here, there is something called a star here. So this star shows you that here the difference between the two scores is significant, whereas here the difference is not that significant, right? So whatever improvement has happened from pre to post can be assigned to working in dyads, and in individuals, if they are working with AR, it's not so fruitful. That is what the inference that can be drawn from here. And here also the descriptive stats is shown, like you have average score here, standard deviation, standard error, and all that, right? So here also we have this one example where this kind of study is conducted. Then there is another example from my own study. So I thought, like, instead of just talking about t-test, let's talk about something more complicated, which is multiple regression analysis. Okay, so this is my own research, where the research is about capturing data from students when they watch a video lecture about difficulty, engagement, and all of that, right? So here we have this tool. So on the left side of it is the video. So student can just play it, start watching it. If they find something difficult, they just click on this difficult button, which is red in color here. If they find something engaging, they click on engaging button. If they find something easy, they click on easy and boring, right? Difficult, easy, boring, engaging. There are the 4 buttons, and students watch and they provide feedback voluntarily whenever they want. So one validity thread, because I think we also learned about validity and reliability. So one validity thread is, what if some students who are highly motivated, they click many number of times, right? And students who are not so motivated, they click very few times. And students who are high performance, and eventually they will engage more into this activity, they'll click a lot. But the students who are not like very good performance, they might not click very often, right? So that is what the thread is. And to understand that and to identify whether that thread really is present, I conducted a study where I collected data on multiple variables. So one is my dependent variable is number of clicks, number of this difficult, easy, boring, engaging, daily clicks any student makes. Then I collected data on student motivation, cognitive, metacognitive strategies, how do they manage the resources, time, other thing, when do they watch it, and all of that. And their prior performance, which is GPA scores I also have, and some pre-test was also conducted before the study. So all these scores I have, and along with this, there is digital natives assessment score survey, which is basically assessing whether the students who are more comfortable and who are more digitally native are taking more or not, right? So I collected data on multiple independent variables which might impact this dependent variable of table weeks, right? So as there are multiple independent variables which might impact a single dependent variable, that's when we use multiple regression, right? And this is multiple regression was conducted, and what I found out was this. So here is the result, right? So we have all these variables, independent variables, and then we have p-values here. So it tells you that p-value is not less than 0.05 given the fact that I'm taking 95% confidence level. Here, all these factors do not have any influence on number of table weeks. Okay, so that is how I established that no matter whether the student is highly motivated, not so motivated, high performer, low performer, student with higher prior knowledge, lower prior knowledge, or someone who is digitally native, more comfortable with technology, and all of that is not going to matter, right? So in that case, I established that this factor doesn't affect it. That is how multiple regression analysis was conducted. So that is another inferential statistics example that I wanted to demonstrate in today's session. Now, you might have heard about ANOVA and all of that, right? So ANOVA is done when you have more than 2 groups. So if you have 2 groups, you do t-test. If you have more than 2, you do ANOVA, which is analysis of variance, right? So again, there is something called as one-way ANOVA, two-way ANOVA. When one-way ANOVA is done, when let's say you have one dependent variable, but multiple, one dependent variable, one independent variable, but there are multiple groups, like 2-3 groups that we have, right? So both independent, dependent are single variables. Two-way ANOVA you do when there are multiple independent variables and a single dependent variable, like this. So for example, I want to answer this research question. Does the AR app improve chemistry scores compared to traditional teaching methods? Now I have 3 different possibilities, 3 different groups. One is the group using AR app, one group using lecture, another group using hybrid, which is using a combination of AR and lecture. So I want to know which group or which kind of design works best. That is where I use one-way ANOVA because it is more than 2 groups and one dependent variable is tested. What if I want to know whether it's not only the teaching method but prior knowledge as well, which might affect their scores? In that case, I have 2 independent variables. One is teaching method, another one is prior knowledge, which might affect the test scores. Right? So that is how. Here now I am to two-way ANOVA because I have 2 independent variables, one dependent variable, and another. So right now I'm not expecting that you will understand all of this. The point is you just need to understand when to use which kind of test. So let's say you have something like this in place, right? Where there is a scenario, like you have one dependent variable, one independent variable, there are 2 groups, independent samples, you will go for t-test if your data is normally distributed. If it is not normal, then you can go for non-parametric. If you have one dependent, one independent, 2 related groups, and it's the same group of which you are pre-post you are doing, then you will do pair t-test and likewise. So basically you go through this table. I'll share the slide deck with all of you. So what exactly I'm trying to do here is this. You have a combination of different variables in your research design. You just need to identify what kind of combination you have, what exactly you are trying to achieve. And based on that, you choose a test. Then you have this parametric, non-parametric based on your normal, not normal. But if the sample size is higher, doesn't matter whether you are doing this non-parametric or not, even if your data is not normal. In that case, parametric should work. Okay, that is one. Another thing is, with this kind of table, you will be in a better position to know what kind of analysis can be done. So this table might help you in doing that. And there are multiple such tables which are also available on internet, so you can go through that as well. So what I'll do is, I think I don't have much time, so I would not go ahead with this unless all of you are okay. And Amrit, you have to tell me whether I should do a hard stop or I can extend for 30-40 minutes, not 30-40, 15-20 minutes. And participants, I think.
Yeah, I think we can extend it to 15 minutes max. If
everyone is okay.
Take queries, yeah.
Okay, fine. Okay. So I'll try to wrap it up quickly. Okay. So the takeaway is this, that descriptive statistics is all about visual displays, numerical pages, but we have to use them judiciously. We should know when to use mean, when to use median, and all of that. And visual displays tells us a lot about the data, not only distribution. It also gives us some hints at whether there are some data points which are very kind of lying outside our entire data set? Are there outliers? Are there certain patterns that we have? Are there two different groups in my data, right? Like some of you said, it's a bimodal data or even trimodal data, if you can call it like that, right? So all of this tells you this kind of things, right? And also this kind of data points or this kind of displays help you to visualize your data better. So one is, it helps you describe the distribution. It helps you to test assumptions for more complex analysis. Like for t-test, some things are needed, like not normal, which test you use. So these visualizations help you with that. And it also helps you to investigate potential relationships if there are two variables. I'll talk about this if we get sufficient time, but this is also something descriptive statistics can help you. Now what I'll try to do is, we so far have talked about the single variable, right? You have single learning gain score, or you have, let's say, survey, some data, but that is single data, right? Which is univariate data. You don't have multiple variables. What if there are two variables, right? How do you kind of go ahead with the visualizations of that, right? So that is I'll try to do, but I'll try to do it very quickly. So the way you can think about it is like this. So in your research, you will have some variables, right? So some of the variables, you can categorize them as categorical and quantitative or numerical variable. So what exactly is numerical or quantitative variable? If your variable is taking some values like 1, 2, 3, 1.5, 2.5, all of that, that comes under numerical, continuous variables, quantitative variable, and all of that. If you have something like groups, like AR group, other group, or then you have gender, male, female, all of that comes under categorical. Then there is something different, which is role of variable. So what is leading to what? So let's say you are saying that AR will improve the representational skills. So AR kind of thing becomes your explanatory variable, and representational skills improvement, basically that score becomes your response variable. So whatever scores you have, learning gain score is response variable, your AR is explanatory variable, or AR and lecture, whatever that group is, right? So then you can combine them and come up with this matrix, and you can say that it can be combined like this. So maybe both of your explanatory and response variable could be categorical, it could be categorical, quantitative, and all of that, right? But let's not get confused with this. We'll actually see one example related to this. So here is one example. So we have a research question, like do different types of research methods, which is lecture-based, project-based, and hybrid, which is a combination of lecture-based and project-based, influence the average test scores of high school students. So you have to quickly tell me, what is the explanatory variable, what is the response variable? Now I can't see my chat because my mobile is dead. So please unmute and speak, or then you just let me know what are the responses.
Yes.
Teaching method is the explanatory variable.
Perfect. And average test scores is the response variable, right?
Yes.
Okay. So in this case, the test scores are measured on a scale of 0 to 100, and 90 high school students were kind of there in the study, and each student's class was classified by teaching method, like whether the teaching method is lecture-based, project-based, and hybrid. Now we have all these data points, right? So we collected all this data, conducted the study, and everything. Now we need an informative visual display of the data to examine the relationship between teaching methods and student testers. What we want to see is how the teaching methods are related to student test scores. Which visual display, according to you, would fit better? What could that display be?
Pie chart.
Pie chart, okay. Why?
That shows the percentage of influence of each and every method.
Okay, but when usually we use pie chart? When we have, let's say, a whole, and we want to kind of identify from that whole what portion is assigned to A, what portion to B, and what portion to C. But now here we have 3 independent groups, right?
Okay.
So can we essentially use pie chart? Any other response?
Stacked histogram.
Stacked histogram, okay. Could you please briefly tell me why that would be a better option?
The teaching method is a nominal variable with 3 groups.
Perfect.
And test score is a is a ratio, is a numeric variable.
Numeric variable.
And we can have three groups in three different colors, and we can show for the three groups what is the average score. Yes.
Okay. So
one more response from Sai. He says vertical line chart.
Vertical line chart. What is that? If you can briefly explain this.
So in one chart they have three numbers, covers lecture, project in percentage wise, hybrid. Like
okay,
that, like
one chart there are three parts, right?
Yes, sir. As Felix had told, like histogram, that they have earlier you showed this, sir. Like in the histogram.
Correct. Okay. Like that. Fine. Now let's think about the first few slides में मैंने जो दिखाया था, where there were like the question was there. If you want to kind of show salaries of employees in an organization, would you use histogram or you will go ahead with box plot? Some of you said histogram, some of you said box plot. So actually, here what is happening? Now you have one categorical variable, which is type of teaching method, and it has like three different groups: lecture, project, and hybrid. So just visualize it like this: you have lecture-based, project-based, and hybrid, right? So if you want to compare scores across these three different groups, what could be the best way to have it? So if they are present on a similar scale, then you can, if you can put them side by side, you might be in a better position to look at the scores, right? And you will see how much scores are varying across all of them. So line chart, whatever you just talked about, that or other ways. What exactly we are trying to look at is how can we differentiate the scores across the three different groups. And for this kind of thing, when you have a categorical variable, which is your explanatory variable, and your response variable, which is quantitative, numerical, continuous, whatever you can call it. So if you have that kind of situation, you should go ahead with box plot. Why? Because it gives you a lot of insights. For example, if you see here, the y-axis is test scores, which is your dependent variable, your response variable. X-axis is your categorical variable. Right? So if you remember about graphs, usually graphs are like that only, right? X and Y. Usually we do it like X changes, then Y changes. So that is how we kind of usually look at it. So that's how the structure is similar here. But now here with this box plot, you'll be quickly able to identify how the medians kind of looking like. And you can also put mean score here on top of it. So you can definitely clearly compare across three different groups. That is not the only thing. You can also compare how the spread is. So this interquartile range, if you look at, you can see that the spread is kind of similar across. It's not like in one case the spread is very large at all. And also the overlaps, if you see across the three, you will see that not much overlap is there in lecture-based and project-based, but there is some overlap in project-based and hybrid. Right? So lecture-based has performed well, next is hybrid, next is project-based. So a lot of insights in a single chart you'll be able to give to your readers. That is one. Now here is another example. So the question is there a relationship between amount of time spent on social media and academic performance in college students? So to do that, I collected data on social media usage, like hours per week, how many users there, then 150 college students का data लिया था. In addition, each student's academic performance was measured using GPA. And then again, for this we need informative display. So what could it be? What kind of display you think would fit better here?
Scatter plots.
Scatter plot, perfect. That's the answer. So essentially what we need is scatter plot. What exactly you can see here is this. X-axis is time spent on social media, Y-axis is GPA scores, and then you plot all those points, and what exactly it means is your explanatory variable is this, response variable is there on the Y-axis, and each point is basically one student, which is a pair of values. So let's say, for example, a student who has spent 5 hours per week is having a GPA of 2.75. Okay, so this scatter plot is telling you how these two variables are related. But the thing is, just looking at it, what can we interpret? Right? So we looked at distribution of single variable where this shape, center, spread tells you like what is the pattern, outliers also tells you. So how do we do it in two quantitative variables when you are trying to explore relationship between them? So we'll quickly try to look at it. So one is your x-axis is explanatory variable, y-axis is response variable. If your data points are like this, so here we can call it as a positive relationship. If your x is increasing, y is decreasing, this is negative relationship. Here it is like very different. It is decreasing first and then increasing. So it's neither positive nor negative, right? So there are different types of directions that we have. So one thing to look at is direction. Second to look at is the form. So here if you look at it, if you just pass a line through this, which can pass through majority of the points from this data set, then you'll see that here it's clearly showing that it is linear. If you do so for this data set, it is non-linear. Here you can see there is a cluster. I mean, there are two different data sets that are clearly visible. There is some subgroup here and another subgroup or cohort which is visible. So when you plot data on scatter plots, where two quantitative variables, two numerical variables are involved, you also can look at the form of it. Lastly, you have to look at the strength of the relationship. So how strongly this kind of thing is related to each other. So if the points are very close to the line, then in that case you can say it is a strong, like very far, you can call it a weak relationship. Okay. So what I'll do is I'll quickly skip this because I don't want to kind of spend a lot of time here because correlation most of you know. Instead, what I'll try to do is this. I'll go ahead with this graphical representation because this is, I think, the important part of a research paper. So graphical representation is basically about telling a compelling and convincing story about your data. And how do you do it? There is a guy called Edward Tufte, and he has a very beautiful book called A Beautiful Evidence, where he talks about graphical representations, visualizations, and all of that. Right? How do they play a role? And there are in total 6 principles, but today I'll try to cover only 3 out of them. Other 3 principles I'll try to share the reading material. So here is an activity. We have a box plot. Now I think so far you have understood and now we are in a position to interpret how a box plot looks like, right? So what can we say about this? So the context is there are some kind of participants who are suffering through asthma, and asthma symptoms are there and they kind of reoccurs like multiple times. So if they are recurring, then it becomes problematic for those people, right? So then what exactly this study tried to do is, this study said there is an air cleaner. If you install air cleaner, let's see what happens. So x-axis you have air cleaner, y-axis you have the symptom-free days, okay? Change in symptom-free days. So 0, this dotted line is basically no change happened. Positive value means symptom-free days increased. Negative values means symptom-free days decreased. So from this box plot, what can we see? So if I install air cleaner, change in symptom-free days if you have to talk about. 0 is no change. Anything positive is there is the number of symptom-free days increased. Negative is those days dropped. What can we say about it? Anything that comes to your mind.
By using the air cleaner, the symptom-free days are improving.
Increasing. Perfect. Very good. So the point is, when air cleaner is used, the symptom-free days have increased. There is an improvement in symptom-free days. Now the question is, compared to what? If we say air cleaner is installed and there is a change in symptom-free day, but what if the air cleaner is not installed? What would happen in that case? So then there is a question of compared to what comes, right? Then you do this kind of visualizations where you have control group and your experimental group. Then you compare the change of air cleaner installation and changes in symptom-free days with this, which is control group or any other type of device that you can think of. And then you say, compared to this group, there is an improvement. That is what this principle is. Show comparisons. So show evidence for a hypothesis always relative to another competing hypothesis. So we have this alternate hypothesis, we have some control group which is related to that hypothesis in a way that even if this is not there, there will not be any improvement at all, right? Always ask compared to what. So if you say there is a change or there is an improvement, the improvement is happening compared to what. So if you want to do that comparison, box plot is the best visualization. Bar chart is also good, but in bar chart you might not be able to show it very effectively. I showed you an example of augmented reality for lines and angles. Their bar charts were used with error bars and all of those. Those are good visualizations, no doubt. But use visualizations which can show comparisons very effectively. Here you can very clearly see the comparison between two groups, right? Now I'm increasing the complexity. So it's the same box plot. Now I'm adding another thing here, right? So now this is about same control group and air cleaner and all of that. But now the y-axis, if you see here, change in fine particulate matter is kind of written in the room, right? So whether the fine particulate matter is increasing, decreasing, right? So what is happening here? So in control group, look at the fine particulate matter. In air cleaner group, look at the fine particulate matter. Then look at both the charts simultaneously. What does this tell you? Can you draw some inference out of it? Some patterns. Yeah. No?
You can go ahead, Felix. Oh, okay. Presence of fine particulate matter is resulting in less symptom-free days, whereas having the air purifier resulting in lower fine particulate matter is resulting in higher symptom-free days. Yeah.
Perfect. Very good. So I think you beautifully explained it. So what this tells you? So basically, it tells you to tell the reader how it works. So you need to talk about the mediating mechanism. You need to have the explanatory framework in place. So here, what is the explanatory framework? You say that if you install air cleaner in a room for people who are suffering through asthma, the symptom-free days will definitely increase. It will improve. Why? Because air cleaner reduces the fine particulate matter in the room, right? So the content of that, or whatever that you can call it, right? So the degree of fine particulate matter or the extent of that or the whatever values you can talk about, those reduce when you use air cleaner. So now what you are doing is you are explaining the change or improvement in symptom-free day, but you are explaining it through the lens of this fine particulate matter, which is nothing but the mediating mechanism. So you install air cleaner, fine particulate matter reduces, and hence you have the improvement in symptom-free days. So always try to have such kind of mediating mechanism or explanatory framework in place. So demonstrate causality, demonstrate mechanisms through which you are trying to, whatever results you have, trying to explain it, right? So what is your explanatory framework for thinking about the question you ask? If the question you are asking is, does installing air cleaner in a room for people suffering from asthma improves symptom-free days? Okay, if that is what you are looking at, you say it improves. So what? Then you have to talk about why exactly it is happening. So one way to look at it is you do qualitative research and combine quantitative and qualitative and do mixed methods and everything. Another way to look at it is collect data on some other variable and use that which is related to your research study, and through that can you explain why this is happening. So it's not only about what, it's also about why something is happening. So that explanatory framework and this causality, everything you will be able to demonstrate if you kind of combine multiple things together, right? And here is the last one. What it shows is this. So it's a scatter plot kind of thing. So x-axis is PM concentration, which is particulate matter less than 10 microns. And this data is from year 1987 to 2000. Y-axis is daily mortality that is happening, right? So what does this tell you? As the fine particulate matter is increasing, what is happening? Or if there is high particulate matter, what happens with the mortality? What does this line tell you? Nothing?
And there is fine concentration of particulate matter. There is a higher density of mortality.
Is it? See, this blue line, if you look at it, it is little tilted towards downside, right? Towards, I mean, it's like this. So it's like particulate fine matter. If it is increasing, then this is kind of mortality rate is less. Is it really the case that particulate matter less than 10 microns are increasing and mortality is kind of less in that case? Okay, perfect. But what if you look at it from seasons point of view? Now I divided the data points as in respect of the seasons: winter, spring, summer, fall, right? And then if you look at it, it makes a lot of sense. Okay, you look at it like actually the mortality is not reducing. When you combine the whole thing together, it looks like the mortality is reducing even if the fine particulate matter is kind of increasing, right? The number of that is increasing. But when you divide it, in that case, you will see that if the season you are taking into account as a variable, then definitely in all the seasons you have more mortality rate as particulate matter is increasing, kind of, right? And you have, like, in some seasons more deaths as compared to other. For example, winter may have more because cold is something that people go through. That is probably the reason because of which the mortality is higher, right? That is how you are bringing in another variable into the picture. So the real world is multivariate. You can't explain a change in dependent variable using just one variable, right? Unless you have control for multiple other things. But you have control for multiple other things, then you have to look for other variables and how those variables might also explain whatever change is happening in the dependent variable. So the real world is multivariate. Show multivariate data. If you have those kind of things in place, if you are trying to look at multiple variables in a particular research study, try to kind of visualize that as well and show it through this kind of visual method. So I think that's it from my side. So thank you so much. Sorry I overshoot, but yeah, I think I would now be happy to take some questions. Amrit?
Thank you, Dr. Pankaj, for explaining it very quickly. I think it was a very comprehensive overview of quantitative analysis methods. So first of all, thanks. And then we have a certain questions. I think on chat there was one question by Mercy Fernandez.
Okay.
Yeah, so maybe I'll read it. So they're asking that if they are doing an experimental design, if they have an experimental design and they are taking samples from two different states to implement their study, then how do they manage the biases which will come with it?
Okay, so a good question. Okay, the first thing is it's a very nice question. So there is, okay, so when we talk about findings, right, we say that we sample the data, conducted the analysis, and this is our finding is, right? But then if you read some papers, and if you specifically read the limitation section of the paper, it talks about that a specific thing. It says that we conducted this study in a particular setting, in a particular region, for this kind of kids and all of this, right? So whatever findings we have, first of all, this kind of population, if it is there, it can be generalized to this kind of thing, right? Another thing they suggest is you collect data from different diverse places. So one is you want to generalize for all the people. So in that case, if you have, let's say, some data collected from Maharashtra, some data collected from UP, some from Kerala and all of that. So what will happen is, so you will have 3 different studies, for example, let's say. And then whatever findings you have, if those findings are close enough, I mean, whatever findings you got are very uniform and not very much difference is there, it's actually going to help you. It is telling you that your findings are generalizable. Because you have, let's say, data points from different places where there are different kind of things happening. But when a particular thing is implemented in different settings, even if geographically it's diverse, culturally as well, maybe, in that case also the similar results are happening. So what you can talk about is this. You can say in different geographies this kind of studies is conducted, and that is how the results are similar, and hence the results are generalized. But this is like very romanticized idea. Okay. Let's come to the reality. Then you might find something which is exactly different. So if you do a study in Maharashtra and then you do a study in, let's say, Kerala, and you find very different results, then basically that gives you another hypothesis or another extension of the research study where you may want to understand and identify what is different in these two settings because of which the results are different. Once you identify that, then you will be in a position to say when this thing works, in under what conditions this thing works, where it works, where it doesn't work. Right? So all those kind of things you will be able to kind of highlight. So the point is, you asked about biases. So actually, there will be few variables which are going to affect your results, right? But that's the reality. We can't kind of get rid of it. But the whole point is, you conduct the studies, you try to identify all the variables which might be impacting the results. And then you try to explain it through the lens of those variables. So I talked about explanatory framework, right? You say in a region, let's say in a state, the improvement is this much, in another state the improvement is this much, other things are similar, prior knowledge and everything. If you are able to establish that baseline, you do that first. Once that is established, you try to identify some other variables, some other parameters, factors which might be influencing this. Then you try to include all those parameters in your analysis in the future. Or with the existing data set, you can kind of do some kind of studies where you see how these parameters turn out in one scenario as compared to other. So now this bias is no more a bias. This is actually an explanatory framework to talk about how exactly something is happening, why is it happening, why it works, why it doesn't work, where it works, where it doesn't work. So now it is actually expanding the area for it. It's kind of expanding the whole thing, like that's how it works. I hope that answers your question.
Thank you, Mercy, for the question. So now we have time for only one question, but we will float a form where you can put your muddy points, and we will connect back again on 30th. Dr. Pankaj will be there, and we will have a live session where you can ask questions which you could not ask today. But we can take one more question and yeah. I guess, yeah.
Sir, for the last graph where the particulate matter and the mortality is the line representing the regression line between the two variables?
Yes, the line is regression line.
Then, since it is very flat, we can say that there is no correlation between the particulate matter between the time series and between the 1987 to 2000 for the mortality. Mortality may occur due to other reasons.
Perfect. So, if you just look at this, okay, so you may say there is no relation. I think it's getting loaded. Just give me a minute. Is it visible now? Okay. So if you look at this, someone may say this line, if you see, which is like, let's say there on the downward side here, right? It's kind of going down. Someone may say there is a very weak correlation, that this is increasing, the mortality is kind of decreasing, right? But if you go here, you see a different picture completely. Now here you see there is some correlation between particulate concentration, matter concentration and mortality, but it is varying across seasons. So now you rightly pointed out that season could be one of the factors, but it's not only season, it's season plus particulate matter. And why particulate matter concentration is more in a particular season as compared to other seasons is something that we can look at. So if we see here, this is like on a little higher side. Now it is here, it is dropping down. So now you can then identify what are those variables which are leading to this. So here essentially we can't say that particulate matter concentration is not kind of affecting mortality. It is definitely affecting. But what is the mediating thing, or what is the factor with which it is interacting because of which it is happening? So that's what the idea is. That's the reason when we say that real world is multivariate, it means that you need to look at multiple variables which are part of that particular scenario, and then accordingly draw inference out of it. So that's what essentially I wanted to communicate.
So we can say that when
Yeah, go ahead.
When we see only the particulate concentration of particulate matter and the mortality rate, we see a limited picture of the smoke. But when we add along with the seasons, we are able to have more clarity when two dimensions are there to understand.
Absolutely. Exactly. I think you very beautifully explained it. I think I was also not able to kind of bring that point forward. But yeah, essentially, that's the thing. That if you just look at a data set, you might get certain picture. But then if you, when you deep dive and you try to bring in different dimensions to it, different variables to it, you will get even a richer picture of what is happening. So essentially, that's what it is. Yeah, thank you. I think, Felix, that was really good. I think you put it really well as compared to the way I was able to do it.
Thank you, sir.
Yeah.
Yeah. So I think we can end the session, and we will float a Google form where you can put your muddy points, any other concerns that you have about quantitative analysis methods, and we will take those up in the next live interaction session, which will happen on 30th at the same time. And Dr. Pankaj will also be there, so you can directly ask questions to him. That would be, I guess, helpful.
Sure. I hope the session has been useful. I tried to cover lot many things, so probably that could be the reason because of which you might find it little heavy. But yeah, I think let's see. I hope it has been useful, and in the like on 30th, right? So we'll meet on 30th and we'll definitely talk about it.
This was definitely useful. I think you covered a lot, and you also gave a very hands-on view of how to use the tools, and it was very relevant to everyone. Thank you so much. And there were some good questions as well. But we'll be also taking up collecting these questions, and I think Leila is asking for more classes on this quantitative. So Leila, what we'll do is we'll move on with the course. And once you start your studies and everything, we'll see if you need more help on quantitative research. And based on that, we'll ask Pankaj to join us again and help us identify some cases, and we'll figure that out once we are deep in your research studies. Is that all right? Is that okay with you, Pankaj?
Yeah, works for me. I'd be happy to help.
Yeah, thank you, Pankaj, for taking out your precious time in preparing the slides to this detail. The session was very engaging, and you can see that so many people are still hanging for questions, answers, and everything. So, yeah, definitely, that's an indicator of good engagement. Thank you very much, everyone. Yeah, thank you, Pankaj.
Thank you. Yeah, bye.
Yeah. Everyone, have a good day. Bye-bye.